So now let's say you are aware of what is disk, right? Hard disk. In the hard disk especially there will be a rotating component, something like CD DVD kind, okay, something like this. That is basically a disk which will be spinning right at high speeds, right? So now let me repeat once again, this is your hard disk, right? This hard disk will have a interface. So here there will be a interface connection, right? And in the hard disk there will be a rotating disk. This is a rotating disk which is something like our disk drive, CD DVD, if you have seen that. And in the center there will be a spindle, right? Based on that it will be rotating at high speeds. So hard disk speeds, normally the rotation, hard disk rotation speeds, right, considered as RPMs, rotation per minute. The hard disk speeds, right, rotation per minute. Okay, and in the hard disk there will be one more important component called header. So a sharp needle kind of thing will be there at the end, right? And this guy will be rotating at high speeds, and this guy also can rotate from here to here like this, right? And this header will be using electromagnetic signals to write to the disk and read from the disk. Okay, it will be using electromagnetic signals. On the disk there will be sectors, cylinders. The disk will be something like it's not so important, but let's try to understand, right? And in this so if you see, right, each one of this is a track, right? Like that multiple tracks will be there on the disk, right? And there will be the smallest place in the disk where we actually keep our data. The smallest place where we keep our data, right, is a so if it is very small size you can consider that as block, right? If it is very small size, else you can call that as sector, block or sector. Anything is fine as long as it's a small size. No. So here there are tracks are there, right? In that, let's say this part is a sector, right? That is the smallest part or a place where we will write our data, right? So data will be written into your sectors, right? Each sector is a smallest physical location basically on the disk. So there will be tracks, so many tracks will be divided like this, right? And it creates a sector here. Every sector will have address, right? And sector will have a small size, for example something like 512 bytes, right? Our modern systems will have 4K bytes, kilobytes, right? Or 512 bytes, right? Sector size I am talking about. So in some systems, right, the sectors, the series of sectors, let's say sector 1, sector 2, sector 3, like this. If you are considering multiple sectors, that multiple sectors can be called as a cluster, Cluster means generally group of resource. Here in this case, sectors as a group, right? That is your cluster here. So let's try to remember once again. A sector, the smallest physical place where actually we write the data. The data can be the sector size, how much data it can hold is 512 bytes, or in the modern systems it is 4K byte. Right? If you are considering a single sector, it's a just sector. If you are considering multiple sectors as a group, you can consider or call that as a cluster. That part is done and deal, right? So this is a physical thing, but every of this sector or the group of sectors will be addressed or identified with a logical address which we call LBA. From the software level or from operating system level, we will be using LBAs to address the location where we kept our data. LBA, logical block address. So here the block can be a single sector or multiple sectors. That sectors are having a logical address that we are calling as LBA, logical block address. Is that clear? Now let's try to understand. You have, let me ask you, I am visible, right? You are able to see me. Done. So if I am visible to you, then let me tell you that, right? So the disk, whatever you are seeing, the hard disk, the rotating disk, right? In that, the smallest part on that we call as a sector, right? That sector will have a minimum capability of 512 bytes. In the all latest hard disks, whatever we are talking about, will have the smallest size, the sector size is 4 kilobytes, 4 KB. Okay, that is the smallest part where we can write our data. So that space, the sector can hold now 4 kilobytes of data. That means if I am creating a smallest file, that file will be sitting in that one sector. Like that, in your hard disk there will be so many sectors based on the size and XYZ. Okay, no? So now that is one thing. So group of sectors are called a cluster, right? And definitely that cluster or a group of sectors will have a identification, logical block address. So your operating system will be addressing the disks, the disk read and write, right, data. It will be addressing using LBS, logical block address. Is that clear? So here I am expecting you to remember that words. One is RPM, the disk rotation speed, basically RPM, rotation per minute. So that will be usually 7K, 10K, means different disks, different make and models will have different speeds, 12K or even 15K. That is the maximum what we have seen till date. So the disk in the hard disk, right, the rotating part will be something like disk only, CD kind of thing. That disk will be rotating at a high speeds. That speed, we measure the speed in RPM, rotations per minute. So the disks will have different speeds. Some slow disks will have 7K and fastest disks will have 15K speeds, rotation per minute. That is one story. On the hard disk, when it comes to the disk, on the disk the smallest part where we keep our data, the smallest space we call as sector. So physically the disk space will be actually divided into sectors, right? Each sector will facilitate a size of 4K byte or 4 kilobytes space it will be providing us. So in the hard disk, if we see, there will be so many blocks kind of spaces, sectors, right? Each sector is capable of, let's say, 4 kilobytes. So if I am referring a set of blocks or a set of sectors, you can call them as a cluster. So the group of blocks or a group of sectors will have an address, LBA, logical block address. I am not talking about here the physical address. Definitely there will be a physical address also, PBA, physical block address. Okay, but here from our operating system side or a software engineering side, we address that every block of data what we are keeping in the disk with LBL, logical block address. So don't go any depth inside, just try to understand and try to remember that way. Okay, now yesterday when we talked about for example mirroring, right, the technique and the technology what we talked about in the mirroring. So we took two disks like this, and two disks logically are seen to the operating system as a single mirror disk, right, where once it is written to the first disk, the same data block is getting copied to the second disk, right. That concept you understood. Now we will go into the next concept is, give me a minute, first I will draw it, then we can discuss about that. Okay, here also I will take an example of you having two disks. Okay, here I will take two disks as an example. Let's say you have disk 1 and disk 2. Okay, so this is D1, disk 1 and disk 2. Now let's understand my operating system or application sending blocks of data to these disks. The blocks is, let's say, A block, B block, C block, D block and so on. If the blocks are coming like this, in this RAID technology which we call striping, the striping technology, here what it do is, it first takes that ABA, and A will be striped here and B will be striped here at the same point in time, and C will be striped here, D will be striped here and so on, E here, F here. So now let me give you an example. For example, to writing a block into a disk, for example, it is taking 1 second time, right? So to write a block of data, so block of data for, let's say, 4 KB of data, a block of data to write to a disk, it is taking 1 second, for example. Now if I have 100 kilobytes of data or 100 blocks, right, then how much time it will take? The simple math, if 1 KB or one block of 4 KB is taking 1 second, then I have like this 100 blocks, it definitely is going to take 100 seconds, right? A simple math. Now I am asking the same thing. I have here not one disk, here this is, if you have one disk and you are trying to write the data, that disk is taking this much time. Now I am saying I have two disks here, disk 1 and disk 2. I have same blocks, 100 blocks I have. How much time it will take? It will take, each disk will be writing 50 here, 50 here, right? 50 blocks here, 50 blocks here, means the actual load is getting shared across two disks. So the actual time it is going to take will be reduced by half. Yes or no? So the same 100, when I have two disks, one set will be written here and one set will be written here, so that it will be completing the task in 50 seconds. Right? We all good here. We all understood, right? That point. That is very crucial for you or for us to understand about striping. Now if I have, for example, 4 disks I have 4 disks. Each disk actually takes 1 second to write one block of data. Now I have 4 disks and I have 100 blocks of data. How much time it is going to take? How much time it is going to take? Definitely it is going to take 100 by, normally it is 100 second, but because that same load is shared across 4 disks, 100 by 4, which is 25 seconds. Are you seeing the speed is getting increased or the performance is getting increased or not. The more number of disks I am adding here for striping technology, right? When we are using striping, our overall performance is dramatically getting increased. Yes, right? Right. So that is how we are achieving here the performance side. So in the mirroring we talked about redundancy, means fault tolerance. If one disk fails, still we will be able to get our data. That is mirroring we talked about, right? So the next one what we tried is striping. So in the striping technology you have, let's say, 2 or more number of disks connected and you apply that striping technology. So the whole space will be shown to the operating system as a single logical drive. The concept is same. Whenever you apply RAID technology, the underlying disks will be shown as a single logical drive. Right? Here the advantages of striping is, the advantages of striping, the advantage of striping is the whole space will be available. Means if I am using 4 disks and each disk size is 1 terabyte for example, I will be having total size is 4 terabyte. Nothing is wasted, space is not wasted. Okay na? And my performance is really increasing. My read and write performance is increasing. Right? So what is the disadvantage? The disadvantage of striping technology, right? Where if one disk is failed, you will lose the data. Is that clear right here? So you have data A, B, C, D. This disk is gone. A, B, C, A in the A, B, C, D, right? B, D and so on is missing and half data only you will be having. That half is also not readable data. So technically you will be losing the entire data. Right? Is that clear? So in R0, a single disk failure, you will be losing the entire data. So this striping technology we call actually R0, RAID 0. The 0 represents here no redundancy. But performance wise, top performance. No other RAID level can beat this R0's performance. Read and writes will be top performance because it is having no overhead of mirroring, no other things. Is that clear, right? You guys got it, right? So for my understanding sake, maybe you understood, but for my sake, let me give you little more understanding. So when I say a block, what is your understanding? What is that you are actually seeing there when we say a block? When I say a block, it is nothing but some series of zeros and ones. Right? Though I call that as A1, whatever I call it, it is series of zeros and ones which is of the block size, whatever the block size used in the operating system or at your RAID controller level. That can be 4 KB, that can be 64 KB, that can be 256 KB, whatever size it is. Right? That many series of zeros and ones combination is a block. Okay? Is that clear? So that can be your file, PDF file block or picture block or anything of underlying storage. Right? Storage is digital. So every file, every data is represented in series of zeros and ones. Right? If that is clear for us, then A, B, C, D, what is missing, what is not missing, we don't know. If the blocks are failed here, one disk is failed here, the entire data will be lost in only striping. When we are using striping technology, the entire data will be lost. You are good here? Now let's say this is a block, right? It is very big, so that we won't be able to work with that. If you want to work with that, right? That is where I just reduce the size of it. Okay. So let's say I have two blocks. I'm talking about two blocks I have, where this block is something like this. Okay. So have you heard something called XOR? XOR. What is it I am asking? XOR. Okay, that is the algorithm which is like in the electronics, right, or in your chips, right, x86 or 8086, 8085, right, there and all you might have heard in your engineering side, XOR. Okay, so what is the behavior of XOR? If I apply that XOR actually the symbolic way, let me write it here. If I remember right from my engineering time, right? So if I have one digit, right, I am applying XOR on this. XOR symbol, if I am not wrong, this one or this one. Maybe this one is right, I think. Which one is right? Any one of you from electronics side or even computer engineer also supposed to know that. Which symbol is correct symbol? Just I am testing your memory. Okay, let's say if I apply XOR here, don't worry about the symbol even, right? So let's say XOR, if you apply the result of this, if the same two digits, if the digits are same, you will be getting output as 0. If the digits are different, you will be getting output as 1. Am I correct? Yes? No? Okay, so the symbol whatever I am using is correct. Okay, good to know that. Then let's say here 0 XOR 1 will be 1 and 0 XOR 0 will be 0. Okay, no? So we are good here. So this is how XOR works. So now let's try the same here. Let's apply XOR and let's get that XOR value here. So 0, 1. If I apply XOR, what is that I'll get? Hello? 1, 1, 1, 1, 1, 1, 1, 1, 1. So all ones we are getting here. Okay, because like it is alternate numbers, right? So this is your XOR value. Now let me ask you the fun part of this XOR algorithm. Now let's try XOR on this X block or with this one. You apply XOR on this 1 0 1 1 1 0 1 0 1. Are you getting it exactly the same? If I use XOR between these two, I'll get this value. If I apply XOR on these two, I'll get A value. If I apply XOR on A and X, I'll be getting the block of B. Can you try that and confirm me once quickly? Can you write quickly like 4 or 5 zeros and ones for A, B and X? So I'm trying to ask you, there are 3 blocks of information, or at least let's say you have 2 blocks. On the 2 blocks you applied XOR and you are getting the third block. Now I am saying the fun part of this, once you get that third block, if you apply XOR on any 2 blocks, you will be getting the third block. If both are 0, you will be getting 0. So don't ask me if all these are 0, these are zeros, you will be getting anyway 0. 0 applied 0, 0. If all are ones, you will be getting zeros here. Same block, see, same is 0. Is it 1 or 0? Same is 0. So if you have 2 blocks here, all 1 1 1 1, here you will be getting all zeros. Okay, but the fun part is on the 3, If you pick any two, you will be getting the other one as the block. So are you getting me, yes or no? So don't worry about any combination. You write any sequence of zeros and ones as first block. Do the same for the second block. Same means I am not asking same series or any series, right? Any series. So you have one series of zeros and ones, and you have B as another series of zeros and ones. Now I am asking you apply on this XOR, you apply. You will be getting the third block. Now you try the fun part. You pick any two, apply XOR, you will be getting the third one. First two you already applied. On A and B you already applied, so that you are getting XOR. Now I am asking, excluding AB, any other combination you try it. AX or BX. If you try AX, you will be getting B. If you try BX, you will be getting A. Confirm yes or no? Right? So that is the fun part you need to understand. This applicable with any number of blocks. But try with 3, that is the simplest possible way of doing it. Okay, so you can have 4 blocks, then apply XOR on the 4 and you will get the 5th one. Now you try any combination of that, you will be getting the next one block address. So this principle we use in the next RAID level. We use this XOR algorithm along with our striping technology. So that is where we are going to achieve one disk fault tolerance here. One disk fault tolerance. By using this XOR, we are going to achieve one disk fault tolerance, that is parity. So this here, what we put X, normally we write here P, means parity. What is it? P means parity. So once you apply XOR or XOR algorithm, the block whatever you are getting, we call that block as a parity block. So this block we call that as parity. Okay, na? That is a parity block. Now let's try to understand with the same, what is this next one? So this one you got it right, R0, we already learnt R1. The next one I am going to tell you is R4. Then I will come back, little different RAID levels, we will talk about it. So to understand that, let me draw that picture once again. Okay. So let me take now 3 disks are minimum required here. I will come back to R0 again, we will talk about little more about R0, but now focus on this next RAID level, then we will come back and learn everything at once along with it. Now in this next RAID level, what is that I am talking about, which is R4, RAID 4. In this, the minimum number of disks are 3 disks. Minimum number of disks are 3 disks. I'll exactly try to fill that whatever we learned in the XOR algorithm, right? Exactly, I'll try to put the same as much as possible, right? Let's come here and see this. This is, let's say I have 3 disks. Now I decided to apply, what is that? R4. So what is that we talked about? There are data blocks we have. Each block I am considering as A, B, C, D, E, F and so on. So many data blocks are coming into my RAID R4. In this case, once I have chosen these 3 disks, disk 1, 2 and 3 disks I selected, and I applied RAID 4 technology on this. So the behavior of R4, the incoming blocks it will take, and it will write A block here, B block here, and parity of AB. Parity of AB. So what is that parity of AB? Can you relate to this? This is the parity of AB. Are we getting it? So here you have a RAID controller. Once that data comes to the RAID controller, The RAID controller will take the first two blocks and applies parity on this. Then it will be actually having now AB and parity of AB. That it stripes across the 3 disks at once. So when you are writing R4, now just try to write R4 is a striping along with parity, or striping with dedicated parity you can write, because the parity is going to return into the same disk. Right, here the parity is going to return into the same disk. Let me write the next disk, next data, C and D, next two blocks, and parity of CD. Okay, like that next blocks, for example, the block is E and F, then here it will be parity of E and F. Any question here? Any question here? So let me repeat once again. I don't know what is that you are asking, R4, R5, that we'll talk about little later. Now just focus on R4. What is R4? Here it is going to use minimum number of 3 disks. Right? It is going to use striping with parity. With what parity? Dedicated parity. That means the parity is going to return to the last disk, like this here. Whatever you are seeing, exactly the same. Okay? This you got it, which is R4, RAID 4. What is that RAID 4? Is using striping with dedicated parity. Can you write that on the note? Okay? Now, let's say, now we already know that. So, for example, in this case, if this disk is failed, how these blocks are, you will get it, or how the RAID controller will calculate these blocks. It just applies the parity on A and parity of AB. You will be getting the B data. Right? So that is where I asked you to just calculate and check it, whether whatever blocks are gone, still you will be able to fetch that data by using the parity calculations here. Right? So your R4 gives you one fault tolerance level is 1, means even one disk fails, still your data will be safe. Read and writes will be happening as it is. Right? And if you replace the failed disk with working one, then rebuilding starts, as we talked about in the mirroring technology. The rebuilding, it builds the data here. So R4 gives you, because it is using striping, it gives a better performance when I compare this with mirroring, because striping always improves your speed. Okay? Is that clear and done? Yes, right? Right, now if you have any questions, we can discuss. So when it comes to R0, how many disks R0 support? Minimum recommendation is 2 and more. That more can be 12, can be 14, can be 16, or even can be bigger numbers based on the RAID controller, whatever we are using in our server. So if our RAID controller supports only this many, then that will be the maximum number. But minimum recommendation is 2 disks you should use, but it even allows you to create with 1 disk also. That is one more thing you should remember. What is it? If somebody is asking in the interview or in the real scenario, you wanted to create a RAID 0, but right now you have only 1 disk. Can I create R0 using this 1 disk? Yes, you can create, but you are not going to get the real advantage of striping. Striping, when it is increasing the performance, whenever you are using more number of disks, right? Yes or no? So this more number of disks definitely is going to increase your performance in R0. So the minimum recommendation is 2 minimum number, or even this RAID controller doesn't stop you to create a R0 with even 1 disk. Okay, if that point you got it, nothing like it. Great. Then R0, you understood only the disadvantage of R0 is if a disk fails in that, whole data is lost. But when it comes to R4, the minimum number of disks are 3, right? And it is a dedicated parity and striping technology to what it uses. So because the parity is, you are writing here in the dedicated disk, and this is not your data, right? This is not your data. This is for protection purpose, you are keeping the parity copy there, right? So this guy is wasting one disk space. Now in the R4, when I create R4, it is n minus 1 into the size of the disk. For example, if you have 1 terabyte data, right? So then it is, if you have 3 disks, 1 terabyte of disk space, then n minus 1 into the size. For example, if it is 1 terabyte, that's what I am saying. So if you have 3 disks here, 3 minus 1, which is just a simple math, right? 2 terabyte will be the usable space. That means your operating system is actually seeing 2 terabyte space to use. When it comes to R0, we talked about there is no disk space is wasted, so the entire space will be shown to the operating system as a single logical drive. Here also, n minus 1 into the size of the disk. Let's say here in this case, you are using 3 disks, but it will be showing as a single logical drive of 2 terabyte size, because 1 terabyte size will be wasted for your parity data. Clear? One disk space will be wasted for your parity. Is that done? Right? Are you learning something? I'm asking you, are you learning something? Is it getting interesting? Hello? Right? Somehow you need to figure out to say hi. Right? I don't know why your audio is not audible. Fault tolerance means basically, right? In the previous sessions we actually talked about little about fault tolerance. So always think about, like, if there are two things and currently working, right? But one thing is failed, still everything in the system is actually not impacted, still it is continue going through. Then it is called 1, or fault tolerance of that system is 1. Now let's come back to R4. R4 is having fault tolerance number is 1. That means in RAID 4, when you apply RAID 4, if one disk fails in that, still it will be in working state. It works as if nothing gone bad. So that is where I say it is fault tolerance 1. Right? So it's a generic term, can be applied anywhere, hardware or software, anything. So if we talk about, for example, if you are aware of this Dockers, right? Dockers are can be configured or created as a fault tolerant n number. Let's say you have like 10 Dockers running. By any chance one Docker is gone, immediately that if you are using Kubernetes or something, right, that will trigger that immediately. One more will, in the fraction of second, it will be spinning one more available. Right? Done, right? Got it? So RAID 1 fault tolerance is 1 again, right? So till now whatever we talked about is R0, no fault tolerance. One disk is gone, entire data is lost. R1, one disk failure means one fault tolerance of R1 is 1. R4, 1. R3, which we are going to talk in next, fault tolerance 1. R5, fault tolerance is 1. Okay? So which we will discuss a little later in the next coming classes, but solidify whatever we learned. Right? Repeat this more number of times so that you will be confidently able to speak about this in the interview. You need to read, repeat and rehearsal it. Okay, this is how the data is there, this is how the parity calculation is happening, and this is how actually it is getting more performance. We talked about, right, how it is getting more performance, right? We talked about that, how it is. If somebody in interview They're interested in understanding your understanding, right? They want to know how you understood, how you can confidently say that is this way, right? So then you should be able to speak about it and draw and show them, right? That is very important. So we are less than a minute, so I'm done if you don't have any questions, right?